All right. Gary, I do not say it is too much for you to ask for the evidence. In fact, I'm trying to walk you through evidence because people have done the math. I would not be sitting here trying to do the math from scratch. We would be stuck at the, hey, maybe somebody should try the math. They have done the math, and the idea of explaining wave behavior in terms of particles, explaining the two slits in terms of scatter, which is what, when it bumps off of dust grains or gas particles when you can see the laser. They have done the math. They have done the math. That's the point. That's when they say quantum mechanics is accurate to this billionth, one in a billionth level, and it's been tested. The numbers have been tested against numbers we can get. They have done the math. Okay, and I'm going to tell you the actual ramifications, which I hope you can acknowledge of what it does, even to the degree that we can't explain it, so it might just be a mathematical model. You can't say that there's no evidence of this, because the important part is not how many universes or anything. The important part is just that it has this wave-like structure in what could be considered a probability space, some sort of a field that relates at least to probability as we understand it. And this can be used to calculate a lot of things about nature, and I'll get into it. One key thing that goes all over. And they didn't, you know, you can't expect CNN and Discovery Channel graphics. People are still looking for the metaphors. So far, you're not getting a lot of those, but there is a lot of information out there. Now, to answer your question, before I get into those other things, a single photon or particle does have a wavelength. And yes, it's the photon's wavelength. I'm going to explain some things you already know. I'm just going to point them out, things you already know, and remind you that, hey, this means that. And you connect it with this, okay? I'm sure that you know what I'm about to tell you, but that you missed thinking about when you were going through this. And by the way, some people are like, well, even explain it to them. Because I think it's good to go through thinking about physical concepts. I mean, I have a lot of facts about physical systems. I have no intuitive grasp of the ideas to reach for those and make them more and more accessible to us until both our intuition changes to understand them, but not so much that it's like a weird false intuition. Just so much as to get a gist, a better fit of how some phenomena works, or all of them if we're unifying phenomena. So, wavelength comes in all, light comes in all wavelengths. Photons are not just visible light. You're thinking of visible light. This is what I'm talking about reminding you. Radio waves are photons. Okay, microwaves and radio waves, we're talking about millimeters and centimeters long wavelengths. Okay. When you say, have they looked at what wavelength? Yeah, you can do it with any wavelength. If you put a bunch of wavelengths at the slit, it'll all get smeared and you won't see the pattern. You have to, to use the math, for the math to come up with that regular pattern, it has to be a regular wavelength. But you can do it with any wavelength, and that's the point. They started off doing it with photons because we couldn't control wavelength enough to do it and measure well enough to measure things with a tiny little wavelength, like actual electrons that have in the quantum field have a very short wavelength. Okay. And then we got to the point where our equipment was able to do that, and they've done more and more and more. And now they're starting to try to do organic molecules, which, in quantum mechanics, even you have a wavelength. It's just so short that it's essentially always collapsed, is the idea. Because your frequency is so quick that you have a very tiny little, almost point-like wave function. Of course, that's somewhat arbitrary because you're not one object, you're a system of objects. But you can be viewed as a system as having a coherent wavelength in some sense, at least mathematically. Okay, so anyway, the thing about the size of objects and wavelengths, it's like it's proportional. It goes back and forth. Basically, if you have a wave, let's say you have a wave going through the ocean, and it's big. It's a long wavelength. The waves are 1,000 feet apart. Something smaller than 1,000 feet is not going to be noticed. And it's not just that it's bigger, but something happens as the object approaches the size of the wavelength. When the object is smaller than the wavelength, basically the wave just goes by as if it's not there. There's only local deformation of the water surface, and it doesn't leave an imprint on the wave. But as soon as you get something bigger than the wavelength, the size of the wavelength, it starts to leave a shadow, a distinct shadow. Now the shadow, because of the bending by the diffraction around the edge of the object, the wave will come back together, but it will be a deformed, the object will have left an imprint. So photons are like this too. So radio waves are very long, so they just go shooting by. Kinds of dust and particles that smaller wavelengths are obstructed by. So the line separation, when you're talking about that, if you do use high energy photons, the further away the screen is, just geometrically, those lines spread apart, so you see line separation. Mathematically, there's an infinite number of lines, but they get fainter and fainter. It's kind of like, you've seen a rainbow, and then you've seen the double rainbow, and maybe I've seen a triple rainbow. Well, theoretically, those go on in infinite orders, but they get so faint that they're, not even necessarily one photon in them. So yeah, with that circular diffraction thing, there's a line way, way out there mathematically. Doesn't mean that, there's a photon, because it might be one photon in 1,000 years would go that far deflected out of a collimated laser. Okay, but it will sometimes spray to the side, and that's the thing. I mean, when you talk about 2 bullets that you could shoot and hit, that just means you get that cone of inaccuracy of the gun down smaller than the radius of a bullet. It's kind of like this wavelength effect, and once you get it there, you can have 2 bullets hit each other. But they don't do it exactly. At some level, you get down to just being atoms off, but it's a matter of principle. Because, yeah, if you're going to exploit this wave-like functionality, the fundamental, something to this part is it has something to do with the inaccuracy. And we spent all this time in science and engineering eliminating inaccuracy, and now it turns out that sometimes if you let there be an indeterminacy, the indeterminacy seems to physically persist for a while, allowing some strange effects. Again, I'll mention some things, it might be in this second video, are really one thing that leads to a lot of things that quantum mechanics does, because there's a lot of oddities. There's that somnoluminescence thing where little bubbles will vibrate with huge amount of high temperature energies and things like this. And if they don't get explained, they don't get explained. If you did explain just that thing, like all the math, nobody would care. It has to explain something else. So that's what we'll get into with quantum mechanics. So why is there 6 lines? It's just because by the 7th set or 8th set, then it would be too dim to see. If you leave it going longer, you see more and more of those. If you left it for an infinite number of years, you'd see saturation in the middle, and I guess infinite, you'd see saturation over the whole thing. So they have calculated the wavelength of these photons, and that's kind of the whole point of quantum mechanics, really. What the quantum physicists do really is all about, well, what is the wavelength of this? And they calculate, well, I'll get into in a minute. Well, let me see. Bullets hitting bullets. Yeah, I didn't say it couldn't be done. I just said, yeah, as you saying. It's not about shooting crooked, but it is about indeterminacy. Now, if it was possible to eliminate and get exact knowledge, and we were ignoring it, that would be one thing. But that's also interesting if it would have a physical effect. That doesn't seem like it should. But we're not doing that. We could get it down as narrow as we want. The thing is, if it's big enough to have 2 slits in it, the thing acts like a wave step. If it's small enough to shoot just through, they've tried this. If you make a laser with accurate enough to just aim it through one slit, of course it goes through one slit. Well, I shouldn't say of course, but that's the particulate nature. You can funnel it through one if you reduce that inaccuracy. Because most light sources are not like lasers. And a tube, you need a really long tube to get, because the angle that you reduce something to with the tube, one is based on, how long it is to how wide it is, so what's the angle of things that can get through it. It's also because some things will get perfectly through it so that they hit right at the edge and scatter, like you've been pointing out. So ultimately, that tube will make a really focused dot, and then it won't blur out slowly, but there still will be specks out there because of this little effect. So it'll never be perfectly cone-shaped, and you'll only know the statistics about the spot. You'll know that it decays at a certain rate statistically, but you can't